Continuing on with our discussion of describing rates in the process of reactions, we want to talk about integrated rate laws. So the purpose of an integrated rate law is to factor in or describe how concentrations and reactions progress over time. So this is really important. We're going to be introducing the aspect of time using integrated rate laws. So if we go back to early on, we looked at some data of showing reaction progress over time, and we looked at, say, comparing different points as a way to figure out or to, say, describe rate. You know, what was the kind of how much was the concentration changing over a set period of time. When we're talking about integrated rate laws, it's a similar idea, but now we're starting to ask, like, what will the concentration be at a particular moment in time? Or say I want to make a certain amount of product, how much time will it take? You know, instantaneous rate laws or instantaneous rates and rate laws tell us how fast the reaction is happening right now, which is very useful. But integrated rate law gives you a different perspective of like, well, if I'm going to reach, say, 2 molar here, you know, right now I can see I'm at, say, 1.5-ish. How long is it going to take until I get 2 molar? How long will I have to wait? Or say if a reactant is decreasing, how long will it last? You know, things like that. How long will it be present? Do I want it to be present that long, or do I want it to be present longer? Right? Control that time if you can diagnose it. In addition to just using integrated rate laws to look into the future, you can also determine concentrations at earlier time. So this is really relevant or useful, for example, the metabolism of drugs in the body, so in, say, in a human body. So we know the kinetics. So metabolism of alcohol by your body is 0th order. And so we know the rate constant of that elimination of alcohol. So if you know, say, what the concentration of alcohol in someone's blood is right now, you could figure out what it was at an earlier time point. So say 2 hours ago or 12 hours ago or something like that. And so you can always go through that because we know how it changes over time. So you can not only predict how things will move into the future, but also reverse. A lot of drugs are eliminated first order by the body. So, and so you can use that to also, say, determine pharmaceutical dosing, right? If I give a certain amount of, say, medicine to a patient, some of it's going to get removed from the body over a certain amount of time. So how long does it need to go until I have the next one? And so that's where, you know, you're told on medicines to take it every 6 hours. That's based around, you know, how much will be gone. You want to balance it that enough is gone that you're not going to get too much in the body, but you don't want to wait so long that there's no effective dose anymore. So you do want to have that kind of restriction. You can also see why when you take medicine, its effect wears off pretty quickly, and it starts to feel a lot less effective because it is first order elimination. It does slow down. A lot of it gets removed right away, and then much lower amounts over a longer period of time. So integrated rate laws can be defined for any reactant or product in any reaction, but they generally can get really complicated really fast. So what we're going to look at is we're going to describe the integrated rate laws for reactions with only one reactant. This isn't actually that limiting. There's a lot of reactions you can use. You can also kind of play around with reactions to make it as if they only have one reactant. So with that, when you only have one reactant in the equation, in the chemical reaction, you're still going to end up with 3 different equations for the different orders. Actually, for any order, 4th, 5th, 6th, gone. We're talking about 0, 1, 2. But all the different orders have different equations for the different integrated rate laws. Yeah, and if you add like 2 reactants, these become really complicated really fast. 3 reactants, especially if you have like, say, a first and a second order, these just become nuts. They become really complicated real fast. So we're going to make our lives easier, get as simple as possible. But you can extend all of these ideas to more complicated reactions. So here is the graph of what the integrated rate laws look like for these single reactant reactions for 0th, 1st, and 2nd order. And so one of the things we can see is these are reactants. And so one of the things, reactant concentration always decreases over time, right? As you move from left to right on the graph, time is increasing, time is passing. And so the concentration of reactant is going to be decreasing, as we would expect, right? It kind of moves slowly down in different ways, but it always gets lower because you're always having some level of reaction. One of the differences, though, is depending on the order, you can have a really high variation. You will note that the slope of the 0th order reaction is constant. It is a straight line. It decreases at a constant rate. That is indicative of the fact that for a 0th order reaction, the rate does not depend on concentration. The rate is always the same, independent of the concentration that you have. For first order, the rate is somewhat dependent on concentration. And for second order, the rate is really dependent on concentration. So you can see that, the rate would be something like it goes down sharply initially, and then it kind of gets a little flatter and a bit flatter. In the case of a second order, it is really sharp initially, and then it gets real flat, real flat, real fast. That is a sign that is slowing down, because you would expect for second order, because the concentration has decreased, you will see a more pronounced effect on the rate. Second order means the rate depends more on concentration. So as your concentration gets lower and lower, you will get a flatter and flatter curve because the reaction slows down more. So if we take a look at this integrated rate law, for 0th order, we can come up with this based on the fact that what the rate order is. Rate law is, the order being 0 means that the rate is just k. You can define the rate as sort of the A over delta T. The negative is there because it's a reactant. So because A is a reactant, remember we need the negative sign, because this, remember, is our overall rate. So the change in concentration phase is decreasing, so we want that to turn positive. You can rearrange that equation, and that's where you get the integrated rate law. We're not going to go into the algebra of deriving our own integrated rate laws, but we can at least see where it comes from, and we just do want to talk about the equation that comes out of it. You'll note we're still using brackets to talk about concentration, and then the subscript denote time. So we always have a 0. So that 0 down there means that is at time equals 0, which is the same as just the start of the reaction, the initial concentration, whatever you started with. And then that T, lowercase t as a subscript, is the concentration at time t. So after that time has elapsed, you'll note it's the same T that shows up right here. If we look at our graph then, the concentration starts at that A0, that's the vertical intercept, and then we can see that the slope is negative k. So this is a straight line. This would be something like B that we have right here, and then the slope is the negative k. That would be the M term that's right there. So when we have our different orders, we can come up with equations for them. We'll see with 0th order, it's just, some subtraction. When we get to first order, we have exponentials that have worked their way in. Second order, we have a fractional form. All of these can be described. These are all the equations for the graphs that I've shown up there, that I'm calculating those graphs using those equations. I made those graphs using those equations. But those are a little complicated, and they can be difficult to work with algebraically and to use. So instead, we used what are called the linearized forms of the integrated rate laws. So linearized, implying that we're turning them into straight lines. So 0th order already was a straight line. For first order, what we do is, instead of plotting the concentration versus time, which was an exponential, we plot the natural logarithm of the concentrations versus time. Then we can see that we do get something that looks like a straight line, where the intercept is then the natural log of A naught, so that would be right there, and the slope is then negative k, just like we saw previously, or just like we saw with the 0th. So we get the negative k, that's the slope right there. So the slope of that line. And so it is, you'll note we are now plotting the natural logarithm of A. This is not the concentration of A that's changing linearly. The natural logarithm of the concentration is what changes. For second order, we plot 1 over the concentration. So we plot 1 over the concentration. We can see that leads to it increasing, because think about it, as the concentration of A gets smaller, 1 divided by a smaller number is bigger. And so this intercept right here would be 1 over A naught, or the A0, that initial term. And then we also do get our slope would be M. And so it is a positive M now for the slope. But these are linear forms. These are much more common forms of integrated rate laws to look at and to use. They're easier to work with, even though you've put in some fractions and some logarithms. If you wanted to solve with the non-linearized forms, you still would have to do that because there's exponentials in the first order. So you'd have to take logarithms. And there's a fraction in the second order form. It's just easier to use the linearized forms because it's just a little cleaner to work with. And they're easier to graph or to think about their graphs. All those slopes. Forgot I had that. So let's apply it. Consider the reaction 2NO2 becomes N2O4. At 500 degrees Celsius, K is equal to 8.0 times 10 to the negative 2 for the reaction. Inverse molar inverse second, sorry, for this reaction. How long would it take for the concentration of NO2 to decrease from 5.0 molar to 1.0 molar?
All right. So whenever we see how long would it take, that always implies we're dealing with a time. And whenever we're dealing with a time, integrated rate laws are what we're going to be using. And so when we want to use an integrated rate law, we want to check a couple things like, do we only have one reactant? Yes, we do. Even then, we can design other reactions so that we can use these laws because they are much easier than anything with 2 reactants. So, okay, so we got that set up. We know we're just going to have the one, so we then need the order. Okay, so it's one reactant, but the equation still is based off the order, but we're not given the order anywhere. But we are given the rate constant. And we know that the units on a rate constant depend on the order. Not all rate constants have the same units, and those units come from the order. And we know that the units are going to be 1 over molarity, the order minus 1 times seconds. And so in this case, because I have molarity to the first times seconds to the first, order minus 1, basically that tells me that the order minus 1 is equal to 1, which tells me that the order is equal to 2, right? 2 minus 1 would just give me the first order. That's reflected in the fact that m doesn't have an exponent when it's written like this, or it's just the negative 1 that's written up there. So I know that this has to be a second order reaction. And since it's second order, that tells me that I would have 1 over, normally we would write concentration A to the 0, or sorry, T, oopsies, equals 1 over concentration A 0 plus KT. But here I can specify what A is. This is going to be 1 over the concentration of NO2 at time T is equal to 1 over the concentration of NO2 initially, or at time 0, plus KT. And what I want to solve for is this T. That would give me how long it is. So the question is, do I have all my other variables? NO2 at time T, that's after some time, that's the 1 molar. The NO2 at time 0, that's the initial, that's going to be the 5 molar. And then the K is going to be 8.0 times 10 to the negative 2, inverse molar, inverse seconds. And so if I plug all those in, I would be able to solve for them and determine what the time is. So we'll go ahead and swap pages. We'll go ahead and plug everything in. I'll rewrite it. So it's 1 over the concentration of NO2 at time t is equal to 1 over the concentration of NO2 that's initial plus KT, plug everything in. 1 divided by 1.0 molar is equal to 1 divided by 5.0 molar plus 8.0 times 10 to the negative 2 times time. I'm going to subtract that, divide by that. T is equal to 1 divided by 1.0 molar minus 1 over 5.0 molar over 8.0 times 10 to the negative 2, is that what it says? And what's going to end up happening is all of these are inverse moles. They're moles on the bottom of a fraction. So all of those are going to cancel out. This is inverse seconds on the bottom of a fraction, so it's going to swap. So my units that I'm going to end up with is 10 seconds. And so we can see that, this allows us to, it's hard to figure out, that if we just figure out what the rate is, or this rate constant, it's hard to know, like, this is the rate constant. But is that big? Is this fast? Is this slow? And so one of the things we can start to develop is some idea that, yeah, this is actually a relatively fast reaction. It only takes 10 seconds to go from 5 molar all the way down to 1 molar, which is pretty fast. It's also second order, which is helping that 5 is going real fast initially. And so it only takes 10 seconds to decrease the concentration quite a bit. And so we can start to make some predictions. This reaction is going to go pretty fast. If you have NO2, it's not going to be around for very long. If you have a sample that you think is NO2, it will very quickly react to become N2O4, which is an important consideration.
Participation 2-3, question 1. You are performing a reaction with compound X, just a stand-in for generic compound. That is first order. K is equal to 3.48 times 10 to the negative 4th inverse seconds. You do not want to let the concentration of X fall below 1.0 molar. If you start with an initial concentration of X equal to 3.5 molar, for how long can you let the reaction run? This is the first question on participation 2-3 due Tuesday, February 3rd at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, you are performing a reaction with compound X that is first order. K is equal to 3.48 times 10 to the negative 4th, seconds to the negative 1. You do not want to let concentration of X fall below 1.0 molar. If you start with an initial concentration of X equal to 3.5 molar, for how long can you let the reaction run? So one of the things about these integrated rate laws is the integrated rate law form of the equation depends on the order. So we've figured out what the order is and then use that to figure out what equation to use. But we can also have an experimental method where if I have a reaction with only one reactant, what I can do is I can measure the concentration of that over time. What I can do then is relate that to, or do some transformations of that concentration data and see what makes it straight. So basically I can see, does the concentration of this change with time? How does it change with time? Where can I make it linear? You'll note we've plotted the concentration of N, the natural logarithm of N, and 1 over N. And you plot them versus time. So the time data is exactly the same. You're just changing what you're plotting as the vertical axis. And we can see that this one is straight. That leads to a straight line. If you take 1 over the concentration of reactants and you plot it versus time, and that gives you a straight line, that tells you it's second order. So we can always use this as an experimental method. This works really well and is a lot easier than determining anything about, working with, say, rate laws or the initial rate method, right? That was a really long process to use the initial rate method. And sometimes you have to use the initial rate method, especially when you don't have single reactant reactions. But in this case, because you only had, say, NO2 as your reactant, you only have one, you can just perform one reaction and measure that concentration of reactant over time. That's going to be also, you're measuring concentration over time. You're not measuring rate. Measuring rate is difficult. So when you're using like the initial rate method, what we used previously to determine order, you have to measure rate, which is difficult. You have to do it multiple times, which makes your experiment take longer. The analysis is more difficult. But this right here, you do one reaction over time, and then you can just basically plot some graphs, see what's straight. and you can see then what the order is. And then you can figure out K in the same way we did previously, plug in some stuff, or you get K from the slope. Forgot. You get K from the slope. You don't even have to do anything else. You get the order, you get the slope, you get all the results from doing an initial rate method, but you know, you don't have to do anything like that. You don't have to do any rate measurements, and you don't really have to do any heavy-duty algebra or anything like that. So that is a large share of when we're working with kinetics, how we work with and describe reactions. When you have a reaction, say for example, A becomes B, you can define the overall reaction rate. So how do you interpret your experimental results? You get that overall rate that is based around, you know, as the concentration of A decreasing because it's a reactant, or the concentration of B increasing because it's a product. So that's just characterizing your experiment. From there, your rate law, if you do some experiments, you can get a rate law, which lets you predict the rate for any amount of reactant. And finally, our integrated rate laws are where we start to factor in time. You will note this is the only equations where T shows up. It depends on the order. So, you know, if you do have whatever order it is, you do need to figure that out before you can use an integrated rate law. But that is how you determine how things are going to change over time, make predictions. You know, 10 minutes ago, what was the concentration? If I know what the concentration is right now, or, you know, in 10 minutes, what will the concentration be? I want to go from 2 molar to 8 molar. How long will that take? All sorts of anything that has to do with a change over time.
All right, first video, full video of the set down, participation 2-3. We've already got a question on. This first set of videos will be covered on the Wednesday midweek homework due at midnight. And then also we got the crystal violet kinetics lab, so we'll actually see a reaction happen, measure how long it takes, and figure out the kinetics of the reaction. So it's pretty cool stuff. Again, we got a pre-lab, lab technique comprehension, and notebook to set up for 11 a.m. on Wednesday. We will be meeting in the lab room like normal again. No participation quiz this week. Other than that, we're just getting started with this set of videos, continuing on with chapter 12. If you have any questions about anything, let me know. If you want to meet before next week's test to talk about anything, the format of the test or material that's going to be on the test, more than happy to. Otherwise, got to keep watching videos, looking for more questions for participation 2-3. I'll see you in the next video.